All right, everybody, so this is the Unit 2 force review for Physics 205. So I'm just going to go through the review and talk you through the correct answers. So for the first part, it's kind of fill in the blank, so this might be more in the multiple choice kind of range, but the first one says the long-range attractive force that exists between all objects with mass is the force of gravity. So gravity is that attractive force that doesn't require touching. For the second one, where it says contact force in a segment of rope or string, that's the tension. Vector sum of two or more forces acting on an object, that's the net force. Another thing you could say is resultant force. F equals ma is Newton's second law. Net force of zero occurs when the acceleration is zero. So if the net force is zero, then the acceleration is zero. That's, again, kind of a result of Newton's second law. An object at rest remains at rest is a section of Newton's first law of inertia. Whenever one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first. That's the third law of motion. Tendency of a body to resist any change in its motion, that's inertia. Perpendicular or force that's 90 degrees to a surface, that's the normal force. In a free body diagram, a dot represents an object and arrows represent forces. Forces are caused by agents. And finally, blank is a contact force that resists motion, that's friction. So those are the terms that were in the fill in the blanks on that first section. Then we start getting into the problems, which is, I would say, the large majority of the test is kind of solving problems. So in the first one, it asks, what's the tension in the rope that is being used to accelerate a 200 kilogram crate upwards at 1.2 meters per second squared? So just kind of going through, the mass is 200 kilograms. Our acceleration is a positive because it's upward, 1.2 meters per second. So if I draw a dot to represent the crate and the forces acting on the crate, we have the tension going up and we have gravity pulling down. And in order for it to accelerate upward, the tension has to be bigger than the gravity. So that seems like a pretty good picture. So if I sum up my forces, it's in the y direction. I have a tension, which is positive, and I have a gravity, which is negative, because it's going the opposite way. And then I can set that equal to m times a. So solving Ft plus Fg is the force of gravity, which is just m times g, so it'd be 200 times 9.8. So 200 times 9.8 is 1960. So I have a negative 1960 here for the gravity, 200, and then I have positive 1.2. Okay? So if I do that math, and 200 times 1.2 is 240. And then I'm going to add 1960 to both sides. Get Ft, which that value is 2200 newtons. So 2200 is bigger than, so kind of just looking through it logically, 2200 is larger than 1960, so the net force goes up and the acceleration would also go that way in the direction. So the acceleration is also up. So that kind of makes sense. 2 is basically the same situation, except this time you are lowering it downward or accelerating it downward. So again, if we draw a picture, free body diagram, dot for the crate, gravity should be the same. So Fg is still negative and it's 1960 and the value. Tension is going up. I want the net force to go down this time. So when I add up my forces in the y direction, or you can do a chart, I have a positive Ft, I still have a negative Fg, and I have ma. The thing that's changed is now we have a downward acceleration, so mass is still 200. Our acceleration is negative 1.2, so that's really the difference. So Ft, the tension is still positive, gravity is still negative 1960. This time my mass is 200. I have a negative 1.2, so it just changes the value to a negative value on the right side of that equation. So it's a negative 240. And then I'm going to add 1960 to both sides. And I get the tension as something like 1720 newtons. So again, just checking it to make sure it makes sense. If this is a positive 1720 and I have a negative 1,960, the downward direction is going to win the tug of war, so the net force is down, which makes my acceleration down, which checks out with my value. Okay, so that's kind of problems 1 and 2, and they were close to each other, so I put them on the same page. The next problem deals with an Atwood machine. So it gives you a picture here and says find the acceleration and tension. So we're finding A and FT for our situation of this Atwood machine, where M1 is 3 kilograms, M2 is 2 kilograms, and there's a coefficient of friction equal to 0.25. So we've kind of done these before where we're gonna select our system. So our system is the whole Atwood machine, and we need to pick the positive direction. So I think the Atwood machine is gonna move that way. So the positive direction of positive acceleration is that way. We, because that's the only way that makes sense, right? Like it's not gonna start magically moving the other way. We label our external forces. So we have the force of gravity on 2, which is an external force. We also have the force of gravity on 1, which is an external force. We have the normal force on 1, which is an external force, and then we have friction on 1, which is an external force. We don't draw the tension in this picture because the tension is internal, and we only deal with external forces. So we've selected our system, we've drawn our free body diagram, now we need to come up with our equations. Just a couple things, we can calculate the gravity, so let's go ahead and do that. So force gravity 1 is M1 times G, so it would be 3 times 9.8. So 3 times 9.8 is something like 29.4 newtons. So that's 29.4. For the force of gravity of 2, that would be M2 times G. So that would be 2 times 9.8, which is just 19.6. In looking at the picture for 1, the normal force on 1 and the gravity 1, they're balancing out. So Fg1 equals Fn1, which is equal to 29.4. And then I can use the friction equation to figure out that number. So the force of friction on 1 would be UFN. So it would be 0.25 times 29.4. And that, I believe, should give you 7.35. So I'll check that real quick to make sure I got that number right. But that's the force of friction, I believe, acting on our box. So 0.25 times 29.4. Yeah, that's 7.35. Okay, so we have all the numbers that I think we need, and we just have to develop our equation now. So summing up the forces that are external on our free body diagram, again, the normal force on 1 and the gravity 1, they're balancing, so we don't really worry about them. So the only thing that's accelerating our system, which consists of 1 and 2, is the gravity of 2 and the friction on 1. And again, we have to base that on this positive direction. So gravity 2 is positive and force friction is negative. So putting the positives and negatives there. And I set that equal to the mass of 1 and 2 together because it's the whole system times A. So I've already have these numbers, so it'd be 19.6, that's positive, plus a negative 7.35, equals mass 1 and 2 together. So mass 1 is 3 and mass 2 is 2, so that's going to be a 5. And I shouldn't have an equal sign there, it should just be 5A. So I need to take that number, divide by 5 on both sides to get A, and you'll get A is equal to 2.45 meters per second squared. So that is the acceleration of our system. So that's the first part, find the acceleration. The next part is find the tension. So with the tension, you have to individualize each free body diagram or separate it out into individual blocks or boxes. So I'm gonna pick 2 because I think that's easier to draw. So we got the gravity of 2 trying to pull down. We have the tension acting between the 2 blocks, acting up. 2 accelerates downward, so that's the positive direction. So gravity is positive and tension is negative. So using some of the forces on block 2 this time, we have the gravity of 2, which is a positive force, and we have a negative tension because that's going the opposite way to the acceleration. And then that's equal to M2 times A. So again, we know a lot of these numbers. Gravity 2 is 19.6. Tension is what we're solving for. M is 2 because that's the 2 kilogram blocks. And the acceleration is 2.45. Okay, so 2 times 2.45 is 4.9. that equals negative ft plus 19.6. So I'm going to just switch these two. So the 4.9 is going to become negative, ft is going to become positive. And if you do that calculation, ft turns out to be something like 14.7 newtons. So we have 14.7 going up or in the negative direction, and we have 19.6 going down in the positive direction. So the difference in those two is 4.9, and that's the net force. And if you divide that by 2, that's the acceleration, which is 2.45. We can check it with the other block. So again, I always try to suggest that you check it. So if we were checking it, we would do that kind of work on block 1. So again, we don't really have to worry about the upward and downward forces on 1 because the gravity of 1 and the normal force of 1 are canceling. But if we draw the forces that are going horizontally, we have the force of friction on 1, we have the tension on 1, and the tension should be bigger than the gravity. So again, the sum of the forces on block 1, we have a positive tension because that's the way it accelerates. On to the right, the friction is negative, and that's equal to M1 times A. So we know these numbers. So the tension we said was 14.7, so I'm going to plug that in. The friction is 7.35. That's equal to 3 times A because the mass of this block is 3. So if I do this math, 14.7 minus 7.35 leaves you 7.35, and that's equal to 3A, and then you divide by 3. If you do that, you get A is equal to 2.45 meters per second squared, which is the acceleration that we came up with up here. So we know that we did it right. So that's just a check. You don't have to do the check, but I always like to do that after the problem or after I get 2 answers to see if I did it correctly. Okay, so that was number 3. Number 4 is our ramp or object on a incline problem. So it says the coefficient of friction, kinetic friction, UK is 0.4. It tells us the mass of the block and the angle theta in the diagram. So we're going to calculate the acceleration, but first we're going to draw a free body diagram. So I'm just going to draw a dot to represent the box. I have the force of gravity trying to pull things straight down towards the center of the earth. The normal force is perpendicular to the surface, and the force of friction is parallel to the surface. So it's going to be kinetic friction. I'm going to draw my axes so that the x-axis is going, the positive x-axis is going down the ramp. So again, kind of just modeling this. And the positive y-axis is perpendicular to that. So the positive y would be going the same direction as the normal force. So there's your free body diagram. Part B is basically just constructing the chart or table that deals with that situation. So we have 3 forces. We have gravity, normal force, and friction. When we add those up, we're going to get the net force. Again, with the chart, I usually try to figure out the positives and negatives. So gravity in the x, that's like the part of gravity that's pulling that way. So I drew that in red. That's going to be positive because it goes along that positive y-axis, or positive x-axis, excuse me. For the y-axis, gravity in the y is a negative gravity y because it's pulling into or the opposite way as the positive, so that's going to be a negative. We're going to go and calculate those later, but we'll finish up the rest of the numbers. So normal force is not going in the x, so that's a 0. It's positive in the y. Friction is going the opposite way to the positive direction of the x, so that's negative, and that would be 0 in the y. The box doesn't accelerate up and down off the surface, so that's going to be 0. And I would expect the box is going to slide down the ramp, so I should get a positive number for that. But I can wait on that and see what happens, but it's going to turn out to be positive. This is the 1% trick where we got to use the gravity in the x and the gravity in the y, and you got to calculate those. So it would be the force of gravity times the sine of theta for the x component and the force of gravity cosine of theta for the y component. Again, that comes from this idea that theta is at the vertical here and the opposite side would be the x and the adjacent side would be the y. So it trades your sine and cosine. Remember, sine slides, so that's in the x direction. So if you do this, FG is just mg, so it'd be mg sine theta and mg cosine theta for the 2 components. So 20 times 9.8 times the sine of 60, and then 20 times 9.8 times the cosine of 60. If you put that in your calculator, make sure you're in degree mode, you should get 169.7 for the X component, and you should get 98 for the Y component. So I can put those in, so 169.7 and 98. From the chart, I can try to add these together, and the normal force is positive 98. Once I have the normal force, I can solve for the force of friction kinetic using the Fun equation. So it would be 0.4 times 98. 0.4 times 98 is something like 39.2. That's going to go in this box. And then it's just adding these two values together. So 169.7 going this way and 39.2 going the opposite way. So if you add those together, you end up with 130.5 newtons as the net force that it experiences. But we want the acceleration, so we're going to do F net equals ma. And 130.5 equals 20a. So we're going to go ahead and divide through by 20 on both sides. And the acceleration you should get is 6.525 meters per second squared, and that's going down the ramp. Or in our frame of reference, it's the positive x direction, which makes sense, right? Because we call that direction the positive x direction. So, so that is the box on a ramp problem that you will have on your review. Okay. The next one is getting into a little bit of the rotational kinematics and solving for torque. So we need to go through and identify all these things. So it says a merry-go-round accelerates from rest. So if it's at rest, the initial velocity, angular speed is 0. It reaches 6.5 revolutions per minute. So that's the final. I'm going to put a star there because we don't work in RPMs. We work in rads per second. So we got to do converting. And then delta t, our change in time, is 34 seconds. It tells you that it's a merry-go-round is a uniform disk, and that's the rotational inertia equation for a uniform disk with a radius of 7 meters and a mass of 31,000 kilograms. We're going to calculate the rotational inertia. So for part A, it's pretty straightforward. I equals 1/2 mr squared. We're just going to plug in those numbers. There's no converting on this one. It's 31,000, 1/2 of 31,000 times 7 squared. If you do that, you get a big number. So it's a long or big rotational inertia. It tries to resist the motion a lot. Rotational inertia is measured in kilograms meters squared. So that's I. That's the answer to part A. Part B wants to know the angular acceleration. So B is asking for alpha. And alpha is a rotational idea. So we're going to set up our table and work through it that way. So we have displacement, initial speed, final speed, alpha, which is acceleration, and time. So 34 is going to go in for the time, seconds. The initial speed is 0 rads per second. And this is where we're going to go back and convert. So convert from 6.5 revolutions per minute into rads per second. So I want to get rid of the minutes in the denominator. And I want seconds, so there's 60 seconds in 1 minute. And then I want radians instead of revolutions. So 1 revolution is once around the circle, and that would be 2 pi radians. So we're going to do that math. So 6.5 times 2 pi divided by 60. If you do that conversion, you should get something like 0.68 rads per second. So 0.68 is going to go in there. And then now we can solve for our angular acceleration. So the equation without delta theta, or the displacement, is the velocity final equals the velocity initial plus the acceleration times the time. So omega F, we know. We know that's 0.68. Omega I is 0. Alpha, the fish, is what we're looking for, and 34 is the time. So that goes to 0. We're going to divide both sides by 34. And we're going to get alpha is something like 0.02 rads per second squared. Okay, so that's not too bad. It's just kinematics with different letters. It's just the rotational version of these same ideas that we had with velocities and acceleration and time and displacement. It's just the angular version, right? For part C, it wants the torque required. So torque is I times alpha. So it's just the number that you got in part A, that big number, times the number you got in part B, which is a small number, and you'll get a torque value, which is still pretty big. It's 15,190 meter newtons is the unit for torque. Okay, so that's number 5. Number 6 is dealing with rotation again. This time it's dealing with a planet. So it's talking about Mars. So it tells you the mass of Mars. So I'm just writing that as mm, and the radius of Mars. So it's talking about the planet Mars and the radius of it and the mass of it. When an object is on the surface of Mars, so if I have some box or object there, we want to figure out what the acceleration of the object is. So we're basically looking for the acceleration on Mars, which is essentially the acceleration due to gravity. That's what we're looking for in part A. So for part A, we think about this, the gravity equation, big G M1 M2 over R squared. We're just changing a couple things. So instead of having M1 and M2, we have the mass of Mars and we have the mass of the object. Those are the two objects. So I'm just changing it from 1 and 2 to M for Mars and O for object. And then R is the radius of Mars. Okay, so that's going to get you Fg, the force of gravity, but we want the acceleration. So if you know a force and you're looking for acceleration, acceleration is just the force divided by the mass. So the acceleration of the object is what we're going to divide by. So if we divide this term by the mass of the object, we just basically cancel out the mass of the object. So the acceleration is equal to the gravity constant times the mass of Mars over the radius of Mars squared. All right, so we're going to plug in those numbers. Again, be careful in your calculator. There's some exponents here. So it'd be 6.67 times 10 to the negative 11th. That's the universal constant, times 6.4 times 10 to the 23rd. All right, so E stands for times 10. That's this part here, exponent 23rd. And then we're going to divide that by the radius squared. This radius is in kilometers. We don't work in kilometers. So 3,390 kilometers into meters. We don't have meters on top. There are 1,000 meters in 1 kilometer. So we're going to multiply this number by 1,000. So it's 3,390, and I'm going to add 3 zeros. 3, and I got to square it. So the acceleration on Mars, which is what we're solving for any object, is something like 3.71 meters per second squared. So that is our acceleration on Mars. So that's that, part A. Part B, we're going to now take the object and we're going to move it so that it is an extra 610 kilometers above the surface. So we've added the radius of Mars and then the radius of the orbit. And that's going to get us our total radius, which is what we need. So our total is what we need. So instead of having this black dot at the surface, now we've moved it slightly above the surface. So we're going to add some to it. All right. So it's a 1,000 kilogram satellite, so that's the mass of the satellite. And then the distance above the surface, that's the radius of the orbit, that we're gonna add. So we need to figure out the magnitude and direction of the centripetal acceleration experienced by the satellite. So it's kind of the same thing that we did in part A, except so we're looking for acceleration, and that's just the force of gravity divided by the mass of the satellite. So again, the mass term, the second term here is going to drop out. So it's just this GMM over R, but R has now changed. So gravity and mass of Mars over the new total distance squared. Okay. So 6.67 times 10 to the negative 11th, that's still the same. The mass of Mars hasn't changed, that's 6.4 times 10 to the 23rd. What's changed is this radius squared. So it's going to be 3,390 plus 610. I picked that number to make it easy. So that's going to be 4,000 kilometers. And then again, you got to convert it. So it'd be 4 million. Okay. So this is going to be 4 with 6 zeros after it. And then you got to square it. Okay. So, so when you add those, or when you do that math in your calculator to get this acceleration that the satellite experiences, which is a centripetal acceleration because it's pulling inward, it's going to be a value of 2.67 meters per second squared. So the acceleration decreased, and it's always towards the center of the circle. It's decreased, right? Because the further you get away, the smaller the acceleration is. So that kind of makes sense. The orbital speed, that's where we use the centripetal acceleration equation. So that's just v squared over r. So if we solve this for v, it'd be v squared equals ac times r. And then to get v, you got to take a square root. So v is equal to the square root of ac times r. So we're going to use our centripetal acceleration, 2.67, and then our new radius of our satellite still is that 4 million meters away. Okay, so if we do that in our calculator, we get a speed of something like 3,268 meters per second. Okay, so we've like once you kind of get this idea of the acceleration is the gravity force divided by the mass of the object that's accelerating, you can find these other things pretty straightforward with these kind of just formula manipulation. This one, part D, asks for how much time does it take to make it all the way around. So it's looking for a time for it to make its orbit. The time for one orbit is called its orbital period, if you want to call it that. Period is represented by the capital T. We know the speed or velocity. So speed is just distance over time. That's the basic idea of speed. It's a constant speed. So if we do that for our idea of the distance is equal to the circumference. So that's 2 pi r. So it's 2 pi r over t. So s equals 2 pi r over t. And t is the orbital period. We're going to solve for t, so it would be t equals 2 pi r over s. So you're going to take 2 pi times that radius, which is still 400 or 4 million. I keep saying 400,000, but it's 4 million, divided by s, which is our speed, which is our answer from part C, so 3,268. And if you do that in your calculator, you get something like 7,690.6 seconds. So that's how many seconds go by as it takes to orbit the planet at that position. The last question, E, is asking what would happen to the speed of the planet if it was now a bigger distance away. So we originally had it as 610 kilometers away, and now it's going to be 1,610 kilometers away. So again, basically you're adding a 1 up here to this number, so it's going to make it 500. So our total in this new one is going to be 5 million meters. All right. So we're going to repeat kind of this process for B and C to solve for the speed or velocity, but at this new distance. So again, as you get further away, the acceleration should get less and less. So if we repeat this, A of the satellite is the gravity times the mass of Mars divided by the radius that it's at squared. So again, it's 6.67 times 10 to the negative 11th. The mass of Mars is still 6.4 times 10 to the 23rd. We're going to divide that by a bigger number now, so we're dividing it by 5 million that time squared. So when you do that, you only get 1.71 meters per second squared. So again, we have now increased and made it a bigger distance away. So we're moving it further out, and now it's out here maybe. And the acceleration has gotten weaker because of that. And then it's just using the velocity as the square root of r times ac or as. So the radius is now 500. I said it again, 5 million meters times that new acceleration, 1.71 square rooted. So when you do that, it's only going now 2,921.9 meters per second. So it has decreased its velocity. So it went from 3,268 down to 2,921. So as R gets bigger, as you get further away, the thing moves slower, right? So that's kind of the idea. Okay, so that's number 6. Just a couple more, 7, 8, 9. So with 7, it's just again, a circular motion kind of problem. So it tells you the mass of a ball swinging in a vertical circle, the radius is that, has a speed of 10.5. We're gonna do a free body diagram. So at the top point, we have forces acting, we have gravity, which is always pulling down, and there's a tension that's also pulling down. In the second free body diagram, the tension is pulling up, and gravity is going against that, it's going the opposite way. So those are our free body diagrams for at the top and at the bottom. Determine the tension in the rope. We're going to need to know the centripetal force here. So that's MAC or MV squared over R. We have all the numbers to figure out the centripetal force, which is the net force, essentially, the total force. So it'd be 0.2 times 10.5 squared divided by 1.5. So if I put that in my calculator, I'm going to get my centripetal force, and I'm going to do that now. So 0.2 times 10.5 squared divided by 1.5, and I get something like 14.7 for that. Okay, so that's 14.7 newtons. I can also figure out the gravity constant or the gravity force. So m times g, so it's 0.2 times 9.8. So that's going to be 1.96. So I know those numbers. Those numbers are not changing because it's a constant velocity, a constant distance, and the constant mass. So these two numbers are both constants. The thing that's going to change is the tension. So it's really just kind of developing a force equation for each of these two parts. So the sum of the forces, which are centripetal, would be the tension plus the gravity. They are both pointing towards the center of the circle, so they are both positive values. We can set that equal to the MAC idea, and we just did that here. So if I plug in these numbers, I got the tension plus 1.96 equals 14.7. So in order to get tension by itself, I'm going to subtract 1.96 from both sides. So if I do that, I get the tension is equal to 12.74 newtons. So the tension is still pulling inward towards the center, but it is not. It's not as big as it's going to be in part B because the gravity is going against that in part B. So it's really similar setup. You got the tension plus the gravity, but this time the gravity is negative because it pulls away from the center, and in the other ones, everything was pulling towards the center, which is the positive direction. Again, you set that equal to MAC. MAC hasn't changed. That's the same number. So the tension is what we're solving for. Gravity is a negative 1.96 in this one. And then we have 14.7 for that. So I'm going to add 1.96 to both sides and get a value that the tension is positive and 16.66. So it is larger in case if we called this A for the top and B for the bottom. It's bigger in the bottom case where it has to pull up more because it's counteracting the gravity as well. So 16.6 versus 12.74. So not too bad on that one. It's pretty quick. The next one here, this one's a little confusing, but if you use this strategy, you're going to be fine on this type of problem. So it's just a free body diagram. There's a mass of 50 kilograms that's hung by two ropes. So I'm going to draw ropes with colors. So force tension 1 is kind of going that way, and force tension 2 is going that way. So tension 2, tension 1, the two ropes, they are counteracting the gravity force, which is trying to pull down. Okay? So the gravity of the object is being held up by those two ropes at these angles. So the angles, it's important that you can see, okay, if I standard X and Y axes, this angle here of 50 is the same as that angle 50, and this angle here is 29. So we're going to use that to help us figure out what's going on. So the force of gravity, again, we can calculate. That's just m times g. So it'd be 50 times 9.8. 50 times 9.8 is 490. So the weight of the object of g is 490. All right. I need to set up either force equations or a table. So I like the table with this type of problem. So I have the tension in 1, I have the tension in 2, and gravity. Those are the three forces that I have in my free body diagram. And when I add them up, I get the net force. Now, in this problem, the object's just hanging there. So it's not accelerating. So the acceleration is 0, which means that the net force is 0. So it's stationary situation. So that means all the forces balance out. Okay, so the acceleration is 0. So I'm going to go through and do positives, negatives, zeros. Tension 1 pulls left, so that's negative in the x, and it pulls up, so that's positive in the y. The tension in the x is positive. The tension in the y is also positive for FT2. And then gravity is going to be 0 in the x, and we said it's negative 490 in the y because we already did that calculation. it's negative because it's pulling down. So the problem with this is I don't know FT1 or FT2. I'm looking for both of those. So I'm going to have to do a little bit of solving a system of equations approach. So in this one, I need to find FT1 in the X, FT1 in the Y, and the same idea with FT2 in the X and FT2 in the Y. So for the X direction, it would just be FT1, which is the whole vector, that's this hypotenuse, times the cosine of the angle, cosine of 50. And then for the tension 1 and the Y, it would be FT1 sine of 50. So I can put that in my calculator and get these values or decimals for the cosine and sine of 50. So this is 0.643 FT1 is what's left there, and this is 0.766 FT1. So I can put them in here. So this is a negative 0.643 FT1, and this is a 0.766 FT2, or FT1, excuse me. I said 2, but it should be 1. So those are like the components of this overall FT1. We can do similar work for FT2. So for this one, it'd be FT2 times the cosine of the angle that it forms, which is 29. And then for the Y, it'd be FT2 sine of 29. Again, those are just going to get you some decimal and then FT2. So for the first one here, you get 0.875 FT2. And for the next one, you get 0.485 FT2. And you might be like, that doesn't seem like I'm getting very far. And that's sort of true. You're not getting very far yet, but we're about to make a breakthrough. So we've just filled in the decimals for the angles that go along with cosine and sine for those particular forces. All right, so now we can develop equations kind of going down, and we can come up with a force equation in the X and an equation in the Y. So for the forces in the X, I got negative 0.643 FT1 plus 0.875 FT2 equals 0. So I can solve this for one variable in terms of the other. So if I take this to the other side, it becomes positive. So I have 0.875 FT2 equals 0.643 FT1. And then I need to divide through to get F2 all kind of isolated. So when I do that, FT2 is equal to, that number is 0.735 FT1. So that is one relationship I'm going to use, and I'm going to use that in the next equation. So if I add up the forces in the Y, that's just putting these together, this column. So I got 0.766 FT1 plus, and that's positive, plus a positive 0.485 FT2 plus a negative 490, because that's the gravity force, equals 0 again. So I'm going to take the 490 to the other side. And I have 0.766 FT1 plus 0.485 FT2. So what I'm going to do is I'm going to plug in this value for FT2. And then I have only one variable that's missing, so 0.766 FT1 plus 0.485 times 0.735 FT1 equals 490. And then I can do algebra and solve for FT1, which is, I'm going to do this now. So 0.766 FT2, the tension, or tension 1, plus 0.485 times 0.735 is, I'm going to check that again on my calculator because I can't read my handwriting sometimes. So 0.485 times 0.735 is 0.356. That's what I think I see, but I just wanted to make sure. And that's FT1 equals 490. So if I add those together, this is like the same variable, so I can just add them now. So I get 1.122 FT1 equals 490, and then you divide through by 1.122, and you get the force of tension in the first row is 436.7 newtons. So that is the FT1 idea. So we found that. That's 436.7. And then now I'm going to use this relationship that we figured out here. And I'm going to take this and plug it in. So it's 0.735 times 436.7, and that's going to be equal to FT2. And that gives you FT2 is equal to 321 newtons. So those are the two values for that. Looking at this and trying to make sense out of it, if you look at like which one is closer to vertical, so FT1 is at 50 degrees above and FT2 is only at 30, like FT1 has to pull more. So this string that I just highlighted in red has a bigger force than this green one because it's pulling up most of the way. So that's why I drew this in that manner in the beginning where the red arrow was bigger than the green arrow. And that's okay if you don't do it that way. If you just have it going along the angles, that's fine. But that's basically the concept here. Okay. So again, just kind of doing this because it's a newer type problem. We drew a free body diagram like we normally do. We set up our table. We had to find components of our two tension forces, and we just used the cosine and sine to figure those out for the x and the y. With that, we just had to kind of keep working through until we got a relationship between 2 and 1, the tension in 1 and the tension in 2. Once we have that relationship, we can plug it into one of our other equations, which is our y equation, and solve. So we basically had two equations with two unknowns. And that's called a system of equations. So if you're familiar with like x plus y equals 10, and then 2x minus 3y equals, 20, then you could solve that and do math like that and get x and y. That's essentially what we did. So like you could call FT1 x and FT2 y. So y and x there, and that would work out the same way. All right. So so that's what we did for number 8. The last one, trying to get through this, it's not too long. This last one. It says a 6 kilogram rifle fires a 0.015 kilogram bullet, and you're asked to figure out different ideas with this. So the mass of the rifle, so I'm going to say R for rifle, is 6, and 0.015 is the mass of the bullet, so MB. The bullet starts from rest, so the initial velocity is 0, and it reaches a speed of 270 meters per second, so that's the final speed, and a time of 0.01. We want to determine the force that the bullet experienced, so the force on the bullet. So that would be the mass of the bullet times the acceleration that the bullet experiences. So we know the mass of the bullet, that's 0.015, that's not that big a deal. The acceleration of the bullet I need to figure out, so again, I'm just going to do kinematics, so delta x, vi, bf, a, and t. So 0, it's at rest, 270 is the final, a is what I'm looking for, time is 0.01, so it's a small time. I don't care about delta x, so I want the equation that is without delta x. We've used this one a couple times so far today. So 270 equals 0 plus a times 0.01. So we're going to divide by 0.01, which is basically the same as multiplying by 100. So you're going to add 2 zeros to this, and you're going to get a is like 27,000 seconds squared. So that's the acceleration, so 27,000. And then you multiply that by 0.015, so just to double check that, 27,000. I got 405 newtons. All right, so the bullet experiences a force maybe going that way of 405 newtons. It wants to know what is the force that the rifle experiences. The rifle is the thing that is sort of pushing the bullet, right? So if this is my bad example of a rifle, so like the rifle pushes on the bullet to the right, the bullet's going to push back on the rifle the opposite way. These are equal and opposite because it's Newton's third law. It's an action-reaction pair. So the force that the rifle experiences is a negative 405 newtons. So that's that. So not too much going on with that. So the force of the rifle, this is just conceptual. It's just the rifle pushes the bullet to the right, the bullet pushes the rifle back to the left. So it's a negative 405. And then we need to figure out the acceleration of the rifle. So again, you're just going to use rifle this time with mass of the rifle and the acceleration of the rifle. So negative 405 is the rifle. The rifle is larger, it's 6 kilograms, and we're looking for the acceleration of the rifle. So we're going to divide by 6, and you get the acceleration of the rifle is like negative 67.5 meters per second squared. So the acceleration of the rifle is much less compared to the acceleration of the bullet. That has to do with their masses. So the bullet is much smaller, so it has a bigger acceleration. So it's a big A. That's for the bullet, if you're doing F equals ma. And then for the rifle, the mass of the rifle is bigger, and that makes the acceleration of the rifle smaller. So that's kind of a visual of Newton's second law and this action-reaction pair where these are equal and opposite forces. So negative 405 and positive 405. All right. So that's the review. Hopefully that'll help you out on the test. Again, the level of problems and types of problems are very similar. So have a good one. I'll talk to you later.